Okay, class time. Anybody have any homework you want me to go over? Did I give any homework?
Was there homework?
Probably not. I think we haven't made it to any
I
yet.
just have a question.
Yeah.
For 5B on the weekly assignment, could you like?
Yeah.
go through the process of that?
I can definitely say something about it. Let's
Let's see, the
see.
due date's already passed on that, right?
Yeah, it was last Friday.
Yeah, that'd be nice to go over the weekly.
Yeah, for now, I'd be happy to go over it in office hours, for people who've turned it in. Okay, this is weekly assignment 3. Is that right?
2.
2.
Which one were you asking about?
5B.
Is it this one? Air compressor?
Yeah.
Yes.
Okay, so it's air, steady state. And you have temperatures and pressures at both. We've used air as a ideal gas several times, so it's a reasonable assumption to think you could use ideal gas here, which means you could find the specific volume from the ideal gas law.
Now is that specific volume sub R, like relative?
No, it's just
Like, because I thought I saw that in the table, and then I used it, and then I was second guessing it later.
Oh, right. That's something that we haven't seen yet. The V sub R and
So that's
stuff
the
like
wrong
that.
one.
Yeah, that's the wrong one. Yeah. Okay, so the diameter, blah blah blah. What's the speed of the air entering?
That's all 5A, and I think it's right. But it was
Okay.
5B that tripped me up.
Okay.
On the CV.
Okay. So if heat is lost, what's the electric power required? Okay. Okay, so it gives you that hint about the CV value. So that means that so you can use, you have the differences in temperature at the inlet and exit. You have Q. Well, it's steady state, so there's no dE dt anyways.
With a CV delta T.
Yeah, I mean, you'd assume that that's what you're going to use somehow.
So that's what I did use.
To get delta U.
Yeah. That's what I used, and that's what I got.
Yeah.
So then really dE dt is not 0, right? Because dE dt.
Right. Let's think about it for a second.
I hope.
Yeah. Okay, so dE dt is equal to Q minus W plus m dot times HI plus VI squared over 2 plus GZI minus m dot times HE plus VE squared over 2 plus GZE. And this Q, so if heat is lost, so heat is leaving the system, so this is going to be negative 500 times 10 to the third. And we can figure out the mass flow rate. We have everything we need to find the mass flow rate.
For finding the mass flow rate. So yeah, because what I did is I went to that air as an ideal gas table to try and find the specific volume.
You can just find the specific volume using the ideal gas law. So PV is equal to RT. So if you use 289 or something for air,
makes sense.
And okay, so you can find all this stuff. Heat is lost. Okay. Phew. So we're saying that that air it's steady state. Boy.
I had to do like some serious research
Uh-huh.
on how to do this. I still don't think I know, but I think that I did it right on what I submitted.
Yeah.
If you want to look at it.
Well, I'm just thinking about is this possible if it's steady state?
Yeah.
Because steady state definitely means dE dt is equal to 0.
I guess I sort of took it to mean as like in part B, like, okay, now we're assuming it's not equal to 0. Right? Because otherwise
If heat is lost.
That specific heat is sort of like you use that to find delta U, right?
Yeah, I mean, there's no other reason that would be in there except to find delta U. I don't know. I'm going to have to think about that before I grade it. And so there's kind of two, things that delta can mean, you know. We sort of use it two different ways. One is the change over time of what's going on inside the system. That's what we can't have if it's steady state. And second is kind of the change over from the inlet to the exit. And with steady state, you can have differences in properties from the inlet to the exit. But the question to me is there a way to use that CV to talk about the difference as you go from the inlet to the exit?
I used it to find delta U, and then I found specific enthalpy using HI is equal, or H is equal to U plus PV, or specific volume.
Yeah. But you used it over the, from the inlet to the exit to find a change in internal energy, right?
And I did change in specific enthalpy is CP delta T. And then I
Specific
used that.
enthalpy
I
is
used that
CP.
in the tables.
Oh, okay.
To get my H final minus my H initial.
Uh-huh.
Oh.
I think that's, yeah. I think that's a good, perfectly good way to do that. I don't know.
It's a tricky one.
I need to think.
A's for everybody.
Yeah, I need to think about that. I'm not really sure that. I need to think about whether CV can be used that way. I'm not. That doesn't feel right to me, really.
Okay.
So I don't know what to say. Let's. So for one thing, yeah. So I'll obviously be gentle when I'm grading that, but let's talk about it later. I should think about that.
Yeah. I feel like once I finished it, I was like, this seems like a reasonable answer.
Yeah.
And I was happy with it.
Uh-huh.
Because when I worked with Jay on this, we got back together and we got like similar answers.
Yeah.
So,
Mm-hmm.
What did you get?
like negative 474.7 kilowatts.
Okay, that's what I got. But
Really?
I just said it was positive because, like,
Right, because it's negative on both
yeah,
sides.
I
because
got
it's-
474.54.
Mm-hmm.
Okay,
Yeah, so we're like,
similar then.
Yeah. Okay. Yeah, I need to think about whether that's the right interpretation of.
'Cause I don't know.
I'm sort of concerned that that's not right. I mean, it's clear that that's the way I was setting you up to do that problem, but
yeah, I don't want to, like, have a misconception because of it.
yeah, right, exactly. Yeah, that's one thing when you write homework problems. One thing you really don't want to do is make people worse because they did the problem. Okay. All right. Any other homework questions or anything? Okay. So we're working on the second law of thermodynamics. Remember, we have a test on Friday. The test won't include any of this second law stuff. So it's just up through control volumes. But we talked last time about the Kelvin-Planck statement. And this gave us some measures for efficiency and ideal efficiency for power cycle, refrigeration cycle, and heat pump cycles. And let's say from this, we can derive an expression that's sort of, think of it as the precursor to entropy, the definition of entropy. And this is the Clausius inequality, it's called. It can be hard to keep all these different definitions and stuff straight. Remember, there's the Clausius statement. But the Clausius statement is not how, you don't use that to derive the Clausius inequality. You use the Kelvin-Planck statement for the Clausius inequality.
This statement is that entropy is always increasing, right?
Not yet, because we don't even know what entropy is yet. We haven't defined it yet. This Clausius inequality gives you a clue as to why we're going to define entropy the way we are going to. And the Clausius inequality, which is from the Kelvin-Planck statement, says for any actual cycle, so both the fact that this is actual and the fact that it's a cycle are important. The integral over this cycle of all the increments of heat transfer divided by the temperature at which heat is transferred around the boundary of the system is less than or equal to 0.
What is that, the partial of Q?
This is like an infinitesimal heat transfer increment. That's all that means. So we're just adding up around the whole boundary, we're adding up all of the amounts of heat transfer that are taking place. Okay? And dividing it by the temperature at the boundary where that transfer is taking place.
So could you say that's like the line integral of 1 over temperature?
No, no, you don't have to think about it that way. It's simpler than that. It's really just there. Whatever your system is, there's a boundary all the way around it, and there's infinitesimal amounts of heat that transfer at every point in the boundary. And the reason we have to write it like this is because the temperature isn't necessarily the same around the whole boundary. Although when we use this, we're going to tend to use it in a simpler form.
What's that subscript? Boundary.
Boundary, yes. And this circle thing is saying it's a cycle. So we're ending up back in the state where we started. And so it's less than 0 if there are any irreversibilities, okay? If the process is reversible, that's when we get this equality with 0. Okay,
so this
yeah.
is pretty much saying the environment is not being affected. Like there's no change in
if it's reversible, you mean, is that what it's saying? Yeah, it means that
because it's 0, there's no change in like the exterior is
Oh.
not being affected.
Well, I'll show you what it means. I think there's a pretty intuitive way to understand what this is saying and to make sense out of it. Before I do that, I want to say, that integral is ugly, but really we're going to think of it as something a lot simpler. We're going to think of it as the sum over think of a finite number of temperature regions on the boundary, and just think of this as the sum of the heat transfers divided by the temperature at that boundary. Okay, so this is something we're going to be able to calculate. And so let me give you sort of an intuitive idea of the Clausius inequality. So imagine a system with a hot reservoir. This is the high temperature. And here's our system. And this is a power cycle that I'm going to use. Now, obviously, the Clausius inequality refers to any cycle. It doesn't have to be a power cycle, but that's what I'm going to draw here. And here's the cold reservoir. And the way a power cycle works is you have heat coming in from the hot reservoir. This is QH. You have heat leaving to the cold reservoir. That's QC. And then you have work being done. Okay. And let's put some numbers on these. So let's say that our hot reservoir is 300 Kelvin and our cold reservoir is 200 Kelvin. Okay. And let's calculate this expression, this integral expression that we use in the Clausius inequality. So the integral of squiggly d q over t around the whole boundary. There are only two places where heat transfer happens. And actually, this is wrong. Sorry about that. We're not going to think of it as a power cycle. We're not going to include that. We're just going to think of it as a cycle that where heat goes in and then heat goes out. Okay, so that's the only place that energy is transferred, is the heat coming in and the heat going out. Okay, well, if it's a cycle, then that has to be the same amount of heat, right? So a cycle says that QH is equal to QC. Let's give it a number. So say we have 1,000 joules of heat for this cycle. Okay. Then this integral is the sum of QH divided by the temperature at H. Let me rewrite this too. So this is QH over temperature at H minus QC over the temperature at C. And so this is, we said these are both 1,000. So 1,000 divided by the hot temperature minus 1,000 divided by the cold temperature. And what you get is now, 3.33 minus 5. So this, you get negative 1.6 repeating. And this is in units of joules per Kelvin.
Why is it minus QC over it?
Because we're just, I'm just adding, our sign convention for heat transfer is positive is going into the system, negative is going out of the system. And so the reason that this comes out negative in this case is because you can't get heat to transfer spontaneously from a lower temperature to a higher temperature. It always has to go from higher to lower. Okay, so the fact that, that simplest idea of the second law of thermodynamics says that the hot reservoir has to be a higher temperature than the cold reservoir. And so when you transfer the heat in that direction from higher to lower, this expression comes out to be negative.
So that's the rate of heat loss from reservoir to reservoir through the system.
No, we didn't lose any energy. It's a new thing. It's saying like, it's so this is kind of the idea of what this is measuring, and this idea is going to be kind of what entropy ends up being. So we didn't lose any energy, but we did take energy from a higher temperature to a lower temperature. Okay. Why is this going to be important? That's kind of where the sort of philosophical part comes in, why do we care where this energy is? We still have that energy, right? Well, think about trying to use this energy to produce useful work, like in a power cycle. Okay. In order to use energy in a power cycle, you need to be able to find a colder reservoir that can direct the flow of this energy through your power cycle to get work out of it. Okay. And so, like, when this energy existed in the 300 Kelvin reservoir, it was pretty easy to use. It was pretty easy to find a cold reservoir at a lower temperature so that we could channel this work to this energy to produce work. Okay. Now that energy is in a colder reservoir, like, okay, well, yeah, we can still find a cold reservoir to get useful work out of it, find 100 Kelvin reservoir, and then we can use that. But now this energy is in 100 Kelvin reservoir. Like, okay, well, that's pretty cold, but I guess we can find a 50 Kelvin reservoir. But as this energy moves from a higher temperature to a lower temperature environment, it gets harder and harder to use it until finally you're like, okay, in order to use this energy, now I have to find something that's absolute zero, close to absolute zero to use it. And now when we put this energy into something at absolute zero, now it's basically lost forever. We can't come up with anything colder to direct that energy. So even though there's energy there, there's no way to use it. That's the idea of the second law of thermodynamics. It's like you've probably heard of people say that entropy is like disorder. What they mean by disorder is we want all the hot stuff together and all the cold stuff together. When we have that, there's only a finite amount of energy. But if we have all the hot stuff together and no energy in the cold stuff, it's super easy to get useful work out of that. Okay? As this energy starts to bring the temperatures of everything close together, even though no energy is ever lost, but you lose the ability to take advantage of that energy. Okay? So like right now in this, like the amount of thermal energy in this room is huge, but getting useful work out of it would be sort of a pain, because all the air surrounding us is at the same temperature or whatever. We'd have to come up with some kind of system, and if all this, eventually, if all the energy is just spread out evenly in space, there's still all that energy, but you just don't have a way to access it, you don't have a way to use it for useful work. McDonald's used to have this thing called the McDLT. Any of you guys remember McDLT? It was really good. They had like the burger on one side, and then they had the lettuce and tomato and pickles on the other side. And it was all in this long styrofoam thing. So you like folded it together yourself. And and so I think of it as like McDonald's lowest entropy hamburger they ever made, because like all the hot stuff was over here, all the cold stuff was over here. If you wanted to use that hamburger to create work as a power cycle, you could do it, A Big Mac, everything's the same temperature. It has the same amount of thermal energy in it, but there's no way to get useful work out of it, And the McDLT was killed by the fluorocarbon thing. Once they had to start using carbon and I mean cardboard instead of styrofoam, then they couldn't make it anymore. So that was the end of it.
Because it insulated it.
Yeah, right. It was in its little insulating thing that like it had half a burger over here and all the toppings over here, and it was in this long styrofoam thing. It was great. It really wasn't as good as a Big Mac in my opinion, but
Making me hungry.
I know, me too. Let's all go to McDonald's. Okay, so I really want you to understand this. The idea that for this thing to be a cycle, you have to have the same amount of energy going in as you have coming out. So that's not what's happening. There's no energy loss. What's happening is you need the temperatures to be different in order to get energy to move. And when those temperatures are different, you're gaining entropy. Okay.
So that number that we got at the end, 1.6 joules Kelvin.
Right. That's nothing yet, but that is related to entropy calculations that we're going to do.
I mean, but really, like, the higher that number is, like, the more potential you have to do work. Is that
the more energy was moved
the more negative that number is, the more you're contributing to this kind of everything being the same temperature, no ability to do work with your energy. Okay. So when people talk about like eventually everything, I don't know what the term is, but you've probably heard what?
Heat death of the universe?
Heat death, is that what they call it? Yeah. So heat death of the universe is just saying eventually, as we keep, constantly this is going on, that energy is moving from high temperature to low temperature. It's slowly bringing low temperatures up, high temperatures down until everything's level. We'll still have the same amount of energy, but it won't be able to do anything.
Is that rate constant?
No, not necessarily.
If I had like a 1,000,000 degree reservoir and a 5 degree reservoir, like it would happen very fast. Versus
right. It's not. But the heat death of the universe, I think, is going to happen
in like
billions of years late, way after the sun has already engulfed the solar system.
The limiting factor on that is Hawking radiation.
Okay.
Like the black holes slowly like radiating into nothing. So it'll be like a few 100 billion years before.
Yeah. Well, the sun is going to engulf the solar system before that anyway, so you don't have to worry about this. Worry about the sun.
In a few short billion years.
Okay, so from this, and I bring this up first because when I give you the definition of entropy, your first thought would be like, where did this random thing come from? This is where it comes from, the Clausius inequality. So from the Clausius inequality, comes the definition of entropy. And it's going to look very similar. So pay attention to the differences between this and what I used in the Clausius inequality. So the change in entropy, capital S, is defined as the integral from state 1 to state 2 of squiggly d q over t around the boundary for an internally reversible system. And I guess in parentheses, I'm going to say now it's not necessarily a cycle. Okay, so this is the definition of entropy. So notice, first, the Clausius inequality requires a cycle. And second, the definition of entropy requires an internally reversible process. Those are the differences between those two things. Who remembers what internally reversible means?
Doesn't have the
Yeah.
irreversibility.
That's right. So I gave you those 7 types of irreversibilities, and internally reversible means inside your system, none of those 7 things are happening. Okay. Outside your system, anything can be happening. War, famine. Okay, so let's do our first sort of calculation. So let's say you have a reversible and irreversible power cycles. And let's say both of these discharge an amount of heat QC to a cold reservoir at a temperature TC. Okay. And both cycles receive an amount of heat QH from the hot reservoir but those temperatures, the hot reservoir temperatures are not necessarily the same And what we want to do is show that the temperature TH prime for the irreversible cycle must be higher than the TH for the reversible cycle. Okay, well, from, just thinking about the fact that for a power cycle, let me draw these, and I think that helps make this clear what we're talking about. So here's the reversible case. Here's the irreversible case. For the reversible, we have this TH. Here's our system. And then we have this TC here. From the hot reservoir, we have QH coming in. And we have QC going out to the cold reservoir. And the result is producing this work W. Okay. And then for the irreversible one, we have TH prime. But the amounts of energy transfer are the same. So we still have QH. We still have QC going to that same temperature cold reservoir. And we still have the same amount of work being done because this is still a cycle. And so in any cycle, you have to have those energies match up. Okay, there's not going to be any change in energy inside the system. So if you have an irreversible case and you want to produce, like you have a fixed cold reservoir and you want to produce the same amount of work, it makes sense that it's less efficient. You need to have a hotter boiler in order to make this work, right? It's going to cost you more energy the less efficient your system is, right? But we want to use the Clausius inequality to show that this is the case.
That's where the greater temperature comes from, is you're having to add more heat.
Yeah, well, it's not more heat, but in order to get the same amount of heat, these inefficiencies cause you to require a higher temperature.
Got it.
Okay, so for the reversible case, the Clausius inequality says, okay, so this is the definition of the Clausius inequality, this integral for the cycle of delta Q over T around the whole boundary. For a reversible case, what is this integral going to come out to be?
0.
0, exactly. And this is the fancy looking form, but really all this means to us is we have two different temperature parts of the boundary where heat transfer is happening. So we have QH over TH minus QC over TC is equal to 0. And we can rearrange this. QH over TH is equal to QC over TC.
that's what I should think of when I think of an efficient cycle. Those being equal.
Yes, exactly. And in the inefficient case, so in this inefficient case, now we have irreversibilities in there. It's still a cycle. We can still use the Clausius inequality. And so this one says that this integral of delta Q over T around the whole boundary, what should this say now? Not is equal to 0. Less than 0, yep. And so this time we have QH over TH prime minus QC over TC is less than 0. All of these values are positive. So I can write this as QH over TH prime is less than QC over TC. And now you can just rearrange this, let's, in the reversible case, if I calculate that TH, we get the TH is equal to QH TC over QC. In this case, since all these values are positive, we get that TH prime is greater than, and it's all those same values. So QH TC over QC. So this has to be bigger. Okay. Any questions about that? We have a couple minutes. Let me just get sort of a formal definition of entropy in your notes. So entropy, it clearly comes from that Clausius inequality. And the change in entropy is equal to entropy at state 2 minus entropy at state 1. And it's equal to the integral from state 1 to state 2 of delta Q over T around the boundary. And this is for an internally reversible process. This capital S is an extensive property. The units of entropy are energy over temperature. This temperature has to be an absolute temperature. The SI units then are joules per Kelvin. Just kidding. I'm not kidding, but that's how I think of it. Just kidding. You're a big loser. Get lost this summer. JK. Like that. And in the tables, they don't list the extensive entropy. They list the specific entropy. And that is lowercase s, and it's equal to the extensive entropy divided by the mass.
See, that confuses me because, like, isn't entropy talking about the system, not a material?
Yeah, I mean, just like it's talking about a material at a specific state. So a material at a specific state, the same way that it has internal energy or pressure or temperature, it has another property that's entropy. Even though this definition of entropy we gave, I mean, in a way, like there's an arbitrary constant in this definition of entropy, because all we ever care about in calculations is changes in entropy.
So that's just like a snapshot of that material in that cycle.
Right. But you can use it to calculate differences. And we're always going to be using it to calculate differences. Okay, well, this way of calculating entropy with this integral thing involving heat transfer, usually we don't want to do that, but there are ways to calculate the entropy without using this integral definition, and so we'll get into that next time. That's the TDS equations. Have you ever seen that in chemistry or anything? T times ds. Okay, so well, we'll do that next time. So it's a pair of equations that we can use for any material under any conditions to calculate entropy changes. I mean, we don't always have all the information we need in it, but anytime you can use those equations, it'll work in any case. Okay, that's all.